All right, so one of the first things we're going to do in a vector field is actually look at how we could use it to model force at a given point and help that or use that to model the work that's done over a given curve. So let's recap because we've done this in Calc 2 before with just a constant force. So in Calc 2, if we had a constant force, let's call that F here, and it's acting on an object while the object is moving in a straight line. Say here, we're going to use a vector d to describe the displacement of the object. Then we define the work to be the scalar component of F. So normally people would say, oh yeah, work is just force times distance. And the difference is if the force is not happening in the exact same direction that you're moving, then we need to look at the component of the force that is moving in that direction. So we're going to take this scalar component, which comes directly from projection here. So the scalar component. And we can just see, just using trig, that this is going to be given by the magnitude. Oops, let's go back here. Magnitude of F times cosine theta. And we're then going to multiply that by the actual distance traveled. And so that will just be the magnitude of d. But if you notice, this is actually a shorthand way of describing this is O, noticing this is just the dot product between F and D. So that's how we define it if I have a constant force moving in a straight line. Now, what if I have a variable force moving over a curve? So we're going to do exactly what we've done all along. Anytime I have something varying over a region is to chop it up and approximate it as if it were constant on small pieces. So let's draw a little picture here. And imagine that we have this curve. Here's the curve C. And then I'm going to have, oh, actually, let's do a different color for that because I was using, let's say that this is my curve. Okay, and then I have some force field that is defined, and it may be defined along the curve, but it may be defined in other places as well. So the key thing is I'm going to be moving along this curve, and it's not the force field that's causing me to move. Regardless, you have some object that's moving. So you could think of like maybe you're on a bike and you're just riding through this path, and then you can think of what's the force of the wind at different points. And so we're going to think about the total work that's being done by that force as we move along this path. But it's not that the wind is blowing you on the bike. You're going to move on your path no matter what, and we're going to calculate the force. Excuse me, we're going to calculate the total work done by specific forces. So we're going to chop up the curve into a bunch of little pieces. And so let's just do some pieces here. And because I'm chopping up a curve, they're going to have length delta S, right? Because you can imagine this is either in 3D or 2D, but you can imagine here's like X, Y, Z. And so we're going to be using S as our variable here. Then, so we'll say that's delta S. Now what I'd like to do is approximate the work that's done by this vector field on the ith piece. So let's pick a little piece here. Let's suppose we're going to call this piece right here the ith piece, like that. And so we'll call this S sub I right here. And okay, so we're going to approximate the work on this ith piece as being approximately equal to, we're going to call this vector right here F sub I. And so it's going to be the dot product between F sub I. And then we're going to need a vector that's approximating the displacement, we'll call it D sub I, as if it was a constant displacement. So I'm basically just trying to do it between those two, between my two little red points here where I've chopped up the curve, and we're going to call this green vector d sub I. Okay, and I was realizing for some reason my writing was not keeping up with what I was saying, but now you can see on the picture. So this, I'm just thinking of what's the work on this segment here, and so I'm going to take the dot product of my force, and I need to figure out a way to find this displacement vector. And so notice that this is a vector that's going in the direction of the curve, and it has length, in this case, delta S. That's how we've been defining this length. And so we know to find a vector, we need its magnitude, which in this case is delta S times its direction. And we know from chapter 10 how to find a vector that points in the direction of a curve like this. It is just the unit tangent vector. So we're going to call, here's my unit tangent vector, I'll call it T sub I. And then we're just going to add this up. We'll do the same idea along all the other pieces, and then we'll take the limit as delta S goes to 0. So you can see we're going to get a limit of a Riemann sum again. Let's write out what we have here. I'm getting a limit as delta S goes to 0. And I'm going to rewrite the integrand in a slightly easier way. Because this delta S is a constant, I can just pull it out front of the dot product and still get the same idea. Or we can pull it out behind. So let's just pull it out behind the dot product. We'll do F dotted with T and then times the delta S. All right, and so this is a limit of a Riemann sum, which means we can rewrite this. In particular, it's going to become a line integral since we're integrating over my curve C, and this will just become F dotted with T, and delta S is just going to become ds. And so as you notice, we have defined this as a limit of a Riemann sum, but to actually evaluate it, we are going to need to, we know how to do line integrals, and in fact, notice what's going to happen when you take the dot product of these two vectors. You're going to end up with a scalar function. It'll be some function of x, y, and z, and then we want to be able to evaluate it by changing variables and converting everything to t, like we did in the last lesson. So let's write out what we know about how to do this from our last lesson. So we're going to change variables by parameterizing the curve. And then we'll plug everything in from there. So let's suppose that our parameterization was r of t is x of t, y of t, z of t. Okay, and then recall, I'm going to need all these pieces for my integral up here. So recall t hat, which is my unit tangent vector, I can get by taking my velocity vector and then normalizing it. And I know how to rewrite ds from last time in terms of t. This is a tiny little distance, which is equal to my speed times a tiny little time. And now I'm ready to substitute everything into this integral up here so that I can actually evaluate. So what we'll get is that work is first we're going to rewrite this vector field f. We'll have to substitute in my parameterization. So I'm just going to write that as f of r of t. And then I'm going to replace my unit tangent vector with velocity. So we're going to take the dot product here, the unit tangent vector, which is the velocity divided by the speed. And then I'm going to replace ds with my speed dt. And so notice what's going to happen. Oh, and t in this case is going to go from A to B. But in this case, this speed here is going to cancel with my Jacobian speed. So this integral is actually going to simplify to be given just by this. And so this is going to be how we actually calculate it. But before we go to do an example, I want to show you that we are now going to take this notation and we're going to come up with 3 different shorthand notations. This is one of them. I'm going to show you 2 more. So here's one shorthand notation, which in practice really means do this. Now we're going to show you 2 other ways that we can come up with 2 more shorthand notations and then what they mean in practice. They are all the exact same calculation. We're still just finding the work by doing this dot product.